for diffusion, we have we have two laws. The first one is Fick's first law. The second one is Fick's second law, and the most accurate one is actually Fick's second law. Okay, and I told you that you have to know the equation, correct? I told you that you have to know this guy and this guy. Concentration as a function of time and concentration as a function of distance. Depth, correct? Depth is the distance. Okay, for diffusion, we have two processes. The first one is pre-deposition, where you introduce the dopant at the very top surface of the substrate. And this one typically has slightly lower temperature, and the time is slightly shorter because we just want to use very top surface. Okay, and then after that we do the dry-in process. Then the impurities, the dopant, are driven in deeper into the substrate. Okay, there are two stages of the process, and so there are many ways of introducing the dopant. Okay, during the pre-deposition stage at the surface. There are many ways, but I don't need you to write all the equations. No need. Okay, I said that I already during my class. I also said, right. As long as you know that there are many ways of introduce the dopant at the top surface of the substrate. Okay, but you don't have to remember all these details. Okay, you don't have to remember all these details. And solvent solubility is important. As I told you that solvent solubility is a function of pressure, correct? So you see the concentration at the substrate, because for this one we typically do put the wafer in a high concentration, in a gas system with high concentration, okay, where you have the dopant. So you can see that initially when you increase the temperature, increase the pressure, you see increase of the concentration at the top surface. But once you reach a certain value, it's saturated. No matter how high you increase the pressure, you don't increase the concentration anymore, dopant concentration. Okay? And this guy is called solid solubility. It depends on what material it is. It also depends on the temperature. Okay? And okay, then we spend some time to discuss the pre-deposition and dry-in and to derive what is the relationship. Okay? I don't need you to derive the equations, no need. As I told you, how we have second order derivatives. This one as a function concentration, as function time, as function of depth. We have boundary conditions, right? Solving these equations, we can get the solution. And for pre-deposition, after this one is error function. And I know I told you we have to remember this one, correct? This equation. And this one is the concentration as a function of depth, and you have to know what is diffusion length, correct? So diffusion length actually is the same. Here is you can see that from this equation, if I give you a diffusion length, the d is already known at a certain temperature and a certain material. You know what is the time is used, correct? If I give you the time, you know what is diffusion length, as I have told you. And pay attention to the details of the vertical axis always. See whether it's a log scale or it's a linear scale. Like in this case, it's a linear scale, but the same thing if we plot in this one is a log scale. And in pre-deposition, you know that because we normally keep the pressure constant so that your concentration at the surface is a constant. Okay? During pre-deposition, I already tested in the class. Okay, and okay, after the pre-deposition, okay, then we do diffusion. When we do the dry-in process, we remove the gas already. We remove the dopant gas already. Now, so your total number of the dopant is already fixed number. Total is already fixed number. Okay, and so if we do. If we have this, actually it's the same equation. If we use the same equation of concentration as a function of time and a function of a function of depth, but we have different boundary conditions. And now, if we solve the equations, we are going to get we are going to get final solution, correct? We're going to get the final solution of this one. This one is called Gaussian profile, correct? So you know the total concentration. This time is equal to 0. Is the one we start to do the driving process. Okay, what is the concentration when we start to do the driving process? It's actually the end of the pre-deposition. The concentration where we start to do the driving process is the same as the concentration we finish the pre-deposition. Correct? From there, you can calculate. Actually, this one, you see, the starting of this is the same as the pre-deposition. That's why when you calculate of this guy, you have to use the pre-deposition time in order to calculate the concentration when you start the diffusion. Because diffusion is when you start the driving. Because driving is done right after the pre-deposition. Correct? So here is the dose. Q here is also the dose. Okay, the dose. Okay, and here after the solve of this equation and using boundary conditions, after driving process, you have this one. As I told you, you have a Gaussian distribution. Okay, and which is pretty important. Gaussian distribution I have mentioned many times. What is the typical pattern of Gaussian distribution? Okay, and Q here is actually what? Is it dopant or what? Is the dose? You know the dose, correct? You know the dose. Oh, you have to know the concentration and the dose. Do you know what the difference of concentration and what is the difference of dose and concentration?
Concentration.
Dose is what you eddy
from the substrate.
Dose is what?
Eddy from the substrate.
Divided by area.
Dose is divided by the area. Concentration is divided by the volume. Correct? During the pre-deposition process, okay, the concentration is the surface concentration is constant. Okay? But during the driving process, the dose is a constant. The dose. Okay? The total number of dopant is the constant, and dose is also a constant. Like here, Q is a constant. Okay, dose is also a constant. But surface concentration CS is not a constant. Because you normalize by the area. Okay, it diffuse in, but the dose is the same. Okay, and you can see that here the concentration is different. But if you, as I told you, if you integrate it, of this one along this direction, then you have the, because this CS is per cubic centimeter, correct? If I integrate in this direction, you basically give per square centimeter. You know that dose, what is the unit of dose? Square centimeter. Correct? So for driving process, the dose is a constant, okay? But CS at the surface is changing. But for the pre-deposition process, the CS is a constant. But dose, of course, is different. Correct? This one I already emphasized many times. Correct? Look at this one. This is log scale. That's why people say, oh, the area is different. Actually, it is because now it's a log scale. That's why it looks different. But if you put it in a linear scale, it will be very similar. Okay? And I have also talked about this guy. This one is diffusion coefficient, correct? In this one, so if we plot log scale, okay, this one I told you this pattern is very important, correct? And you have to remember this equation. And I have actually asked you guys to derive this one. I ask you guys to please do the log of this one and how it looks like. And if you do a log, correct? And I plot that curve of log of this square root of diffusivity as a function of 1 over t. This is 1 over t. It's not is not t. 1 over t, you have straight line. Correct? So the slope gives you what? What is EA? Guys? What is the EA? What is it called? EA is activation energy, correct? The slope of this one will give you activation energy. Okay? And how, if I give you two different things and plot them, and how you are going to differentiate them, which one has a higher slope, which one has a higher activation energy? This one you need to know, and I actually tested you. And here we summarize different materials, correct? You can see that the diffusion coefficient as a function of 1 over t, you can see it's a function of different materials, and also is a function of temperature, correct, right? The same material, if you have different temperature, you have different diffusivity, but you also see different materials, you also have different diffusivity, correct? So diffusivity is a function of material, is also a function of temperature. Okay? So this one you don't need to know, okay? Just skip, okay? E, skip. Even for the push effect, skip, okay? But this one you have to know, or solvent solubility, as I told you just now. What is solvent solubility, correct? Yeah. If I give you a graph, you need to read how to read the graph. You also have to know. Okay? Solvent solubility of this one, of this atomic illustration, skip. Okay? This one. Skip, skip. Skip or skip. You see? Wow, skip it. You see, you save so much energy, correct? You see FGH or skip. You see? Now you save so much time. Okay?